okay to the questions. Okay, so let's get back to the lecture. So the reason that we had that quizzes for today is that without having that understanding of that part, you won't be able to follow some details of today's lecture. So we briefly reviewed the basic ideas about the conditional distribution things and also the quizzes. So for these first three questions, expressing the py with respect to the py given the x and the px, this is like just a matter of like using the marginalization and also the base rule, right? So based on that, now we can express the py as the integral like multiplied by multiplying py condition the x and the px, right? And also the second question is the same thing, but just simply replacing x into the x0 and also the xt condition, right? And since I also said that this conditional distribution is the same as like dropping the xt, because xt is also sampled from the x0. So adding the xt, the condition is not providing any extra information to the y, right? So based on this fact, we can also say that the probability of the y conditioned by xt is also having this form, right? Actually, this conditional distribution is the things that we are going to calculate into this lecture. And also from the 2D's formulation, now we can also compute the expected value of the x0 given the xt, which was denoted as the x0 by t in the previous lecture, right? And from the 2D's formula, that we could also basically calculate this.
Sorry, Professor. You're not showing the slides right now.
So you're not seeing my slide? Oh, sorry. Can you guys see my slide?
Yes.
Yeah. So let me get back to the first things. Yeah. So the py is basically can be derived from the marginalization, the base rule. And also the py conditioned by xt can be have this formulation based on the things that we have seen in the previous slide. And also from the 2D's formula, now we can calculate the expectation of the x0 given the xt, which is something that you will also need to implement in the assignment 5, right? So based on the 2D formulation, now we can calculate the expectation of the x0 from the xt like this. So please remember these two. So these are basically things that we are going to calculate in the many of the parts, in the many of the applications. And given this fact, can everyone see my slide and hear my voice? Seems like the connection is unstable. Yes. Yeah, from this, like what we wanted to do is that we are now seeing that py conditioned by x0 is basically having this form. And also the px0 conditioned by xt, we are also modeling this as kind of the Gaussian distribution based on the expected value of the x0 given the xt here, right? So since we can basically calculate the mean here of this specific conditional distribution, it's basically matter of like basically we are defining the variance here. So we are specifically defining the variance as some kind of some isotropic the variance here. And given all these facts, now we can calculate the conditional distribution of the y given the xt, right? Which will basically having this form, because now we are seeing this specific the prior distribution and also the likelihood distribution. And when you combine these two, based on the properties of the conditional the Gaussians, now we can see that this specific the conditional distribution of the y given the xt should have this mean and the variance, right? So these were basically the answers for the quiz. Any questions on this? So your participation scores will not be counted based on whether your answers are correct or not, but based on whether you submitted some reasonable the answers. So if you submit blank the page, which will not be counted as that you submitted. But if you at least like try to solve the questions, then it's okay. Then it will be counted as that you participated. Okay. And are you also seeing the slides of the lecture 12? I just post the link in the lecture 12 the channel. Okay. Any questions on this? A is a matrix. Here, it can be a scalar or a matrix. Okay, so these are some kind of the details that we are going to see in the today's lecture. So for today, we are going to basically wrap up our discussion about some kind of the guided generation. So we have seen some multiple the cases in terms of doing some sort of the conditional generation, right? So the first example was about the control net, which is basically fine-tuning some kind of the pre-trained diffusion model with some kind of the conditional input, especially when you have some kind of the pairs of the input condition and the outputs. But when the scale of that kind of the pairs is basically not that big, we are basically fine-tuning some kind of a pre-trained diffusion model in a way that we are basically copying the encoding part to basically encode the condition as well. And was after basically we fine-tune the models, we could basically able to produce some kind of the multiple some conditional the outputs, like taking the sketch as the input and the human pose as the input, right? And this was the case that we are basically assuming that there are some kind of the data set for the input condition and the output pairs. For those kind of the cases that we could consider fine-tuning the model. But if we do not have any kind of the data to fine-tune the network, then we could also use the SDEdit approach, which is basically starting from some kind of the slightly like less realistic some data point, like the sketches in this case, and then running the forward process and the reverse process again in a way that we can find some kind of the closest, some realistic the data point from the given the unrealistic the condition. So this was the example of the training-free the conditional generation. And also for some kind of the in-painting the cases specifically, we also discussed the idea of the repaint, which is basically the case that we are assuming that we are having a image and the mask. And then for the foreground region, we are running the denoising the process, and the background region, we are running the fold the process, and then combining the outputs that every time step t, and then basically repeating this kind of some combination. So this was some kind of very practical, some engineering the idea in terms of that we can do also some in painting. But this was also very interesting, the example in terms of that we can now utilize some kind of pre-trained diffusion model, not only to produce the entire the data points, but also to basically fill some kind of the missing region, while basically preserving some kind of the other the background part. And this could be done without basically fine-tuning the network, but just using some kind of, fine-tuning the network for that specific purpose, but using some kind of the pre-trained the diffusion model for the entire data set without any kind of conditions. And we are going to see some kind of some general the framework to solve all those kind of things. So the problem that we are going to see is basically the problem that is called the inverse problem. Which is the case that we are basically having some kind of the measurement of some kind of the data that we want to see at the end. But the measurement is basically not some kind of the data, directly seeing the kind of data that we want to see, but basically some kind of observation through some kind of the angle. So let's say basically we are having some kind of the y here, which is basically the observation of the some causal factor of the x here. And the only thing that we know is that basically the y can be computed by applying some kind of some operation, which is the a function here. So we are basically seeing the x, which is the data point that we want to see, through the angle of the function a, through the operation of the a here. But the only information that we are seeing is basically not the x, but the y. And also there can be some kind of the corruption in the measurement, which is basically adding this kind of some Gaussian noise here. So given the y, and also when we do not know the information about the z here, how can it recover the original the causal factor x? Given also the information about the a function here, is basically the inverse problems. So again, basically the information that we have here is that we are having the measurement y, and also the information about the function a here, which is basically some kind of operation, which is basically applied to the causal factor the x. So we know the y and the a, but we don't know the x and z. So z is basically the corruption, some kind of the noise added to the hourly measurement. So in some of the cases, the sigma there can be zero, which means that there's no noise. But we are also having the y and the a, and given that, how we can get the x information here. So here basically what you can see is that if the a is basically a linear function, which means that if a becomes just like multiplying a matrix to the x, and also the matrix is basically the full rank the matrix, then we can directly solve this the problem by just taking the inverse of the a matrix to the y, right? But for most of the cases, this is not the kind of the deterministic kind of the case. Like it's underdetermined some kind of problems that there can be some possible multiple dx from the given dy. So how we are going to solve this kind of problem is the question here. And there are tons of such kind of the cases. So some of the applications that we are going to briefly see is that, like for example, for especially for the images, we can think about the cases that we are having some kind of the blurry images like this, as you can see at the right bottom, right? So given the blurry images, how we can recover some kind of clean images that basically the cost, basically the blurry images from some kind of blurring the operations. So in this specific case, we can think about the basically y becomes some kind of the blurry image like this. And if we assume that basically the blurriness comes from some kind of the specific, some kind of the blurring the model, for example, like applying some kind of Gaussian corner, the convolution of the Gaussian corner becomes the a function here. So when you assume that the blurry image comes from that, we are basically applying some kind of Gaussian corner with some kind of convolution over the entire the image, then we can think about that the convolution, the operation becomes the a function, and also we are having the blurry image, right? So given these two information, we want to recover the original, the clean image. This can be like one specific example. And also for the useful resolution. So let's say we are having some kind of the very low resolution images, like some pixelated images, as you can see on the left-hand side. And we want to basically recover the higher resolution images of that specific given the input, right? Then we can think about like how we can basically run the other way around from the high resolution image, how we can get the low resolution image. So that becomes our the a function. That's basically some kind of the interpolation, the function like bilinear or the bicubic, the interpolations. So given that basically the interpolation, the function, and also the low resolution image, how can you recover the high resolution image? Is basically the super resolution, the problem. And this is not only the problem for the images, but also for the 3D or some kind of many other the signal, audio, video, many other things, right? So there was super resolution can be like one application. And also the other application is the in-painting and the out-painting. So these are like all very nice results that we are basically removing some of the objects or some kind of some clutters or some occlusions in the images by having some this kind of the masks over the images. So given that the image with the background, what should be basically the function in this specific case? We have seen this case before, right? So in the in-painting case, like what should be the a function here? Yeah, it should be the masking function for the background region, right? In a way that we are only taking the background region from some kind of the causal factor, the data point, and then matching whether this is the same with the background the information that we have, right? So it should be basically the masking the operation for the background region, right? So these are some examples in the image processing, but also for the many other things. Like the other example might be the tomography. or some many other 3D reconstruction cases. So tomography is basically a technique that we can see for the CT reconstruction or the MRI reconstruction for many medical imaging the cases. So these are typically the cases that we are having some kind of some projections of the 3D object into the multiple views. And the projections are typically based on some kind of the volume rendering, which basically means that the rays basically penetrate through the object and accumulating all the information through basically the interactions with the particles in the object. And typically, the way that we can actually recover the original the 3D object from the projection is basically doing another way of the accumulation from the 2D to 3D. So this is basically one example that we are accumulating some kind of the information through the penetration of the ray for each of the view. And then we basically do the accumulation in the other way around from the 2D to 3D. You can see that now we can recover the original the 3D information in the 3D space. So this is basically the typical technique that we can see in the tomography. But also for those kind of the tomography reconstruction, we can get some more accurate the 3D reconstruction outputs when you have some multiple views. Basically, many protections from the multiple different the views. For the cases that when you have some kind of the sparse views, we also will need to basically solve this kind of the under deterministic the problem in terms of that there can be multiple the causal factor X given the some kind of the images from different views. So that's kind of thing. For the inverse problems, the thing is that the solution of the problem may not be unique. So that's basically why we need to, there's somehow literally some kind of the conditional degenerate models in terms of that we can generate some kind of the realistic the data point that also satisfies the condition given as some kind of the measurement y the problems. So in this case, basically what we are going to do is that as we have discussed in the previous lectures, like diffusion model is like all about basically how we calculate this core function, right? So once we are able to basically compute this core for the data point, for the noise data point xt, based on that, basically we can run the denoising process using this core to get some kind of a realistic data point. So let's assume that we are having a kind of the pre-trained diffusion model, which is basically giving some kind of the information about the score of the noise data point xt. But now we want to basically do some kind of the conditional generation in terms of that we are sampling the xt given the condition of the y. So when you only have the information about the score of the xt, unconditional score, right? How we can also calculate the conditional the score given the y here, right? So this is basically what we are going to do. And from the base rule, basically what we can see is that if we consider the condition of the xt conditioned by the y, this can be actually seen as kind of the summation of like these two. The unconditional noise, the xt here, and the score of the y given the xt. So basically what we can see is that while basically we want to compute the score of the xt given the y, to compute this, especially like when you assume that the unconditional noise is basically given, the only information that we need to know is basically this score, basically the condition, the score of the y conditioned by the xt. So if we can compute this specific score, now we can do some kind of the conditional generation based on the information of the unconditional score of the xt here, right? So the key in the solving the inverse problem using the diffusion model is basically all about basically computing this part, right? And actually, in the previous lecture, we discussed like how we can calculate this part. So do you remember like what was the names of the technique like computing those score of the y conditioned by xt? We discussed the two techniques for this. if you did the assignment 2, then you should have known this. Yeah, it's basically classify guidance and classify free guidance, right? So the idea for the classifier the guidance is that when the Y is basically labeled for the some kind of images, we could consider basically modeling this specific score, the Y conditioned by XT, as some kind of the gradient of the log of the output of the classification network. So the idea for the classifier, the guidance is that now we are training a classifier, which is taking the XT as the input and basically predicting the class, the label for the image, and taking the gradient of the log of that. So that becomes basically the score for this term, right? So this was the case that when we specifically have the Y as kind of labels for the images, we are basically additionally training another lead network, which is the classification lead network, and then computing this from the classification lead network, right? And the other way around, especially when the Y is basically not a label, but any kind of condition, was to basically also training the network in a way that we can also predict the conditional noise as well. So the idea for the classify free guidance was to basically now modifying the architecture of the noise prediction network in a way that it can take the condition as well as the kind of input. So we could basically provide the null condition, which is the case that we are predicting the unconditional noise. We're just taking some kind of condition in a way that we can take the condition of the noise. And since basically we are having this kind of the relationship between the noise that we are predicting and also the score function here, we could consider basically combining these two, the output of the unconditional and the conditional the noise, which becomes some kind of the modified the noise in the classified free guidance based some kind of the generation. And this was the case of the when the weight is the 1, but we could also do some kind of the extrapolation by just setting the lambda to be greater than 1, right? So these are all the examples that we discussed before. The downside is that these all basically require to have some kind of the some training data, including the pairs of the conditional input and the outputs. So that's the thing. If we have some kind of the sufficient amount of the training data for the pairs of the conditional input and the output, then we can either consider like train using the classifier guidance or the classifier free guidance, train the neural network to predict this information, this score of the Y conditioned by the XT using the neural network. But here the question is that when we do not have some enough amount of the kind of the data, the pairs of the conditional, the input and the output, then how can we still compute this property? So if we think about the cases of like the in painting, where some kind of the super resolution, either we can consider basically collecting lots of such kind of data, like taking some kind of the masks in the images, or just taking some low resolution in the images, and training this kind of the network, right? But without like having like some fine tuning, can you still do the kind of solve the inverse problems as well? So we are going to briefly discuss the idea for that. So here the thing is that how we are going to model this specific score without the training or without the fine tuning. So let's think about some easy case first. By the way, after basically seeing all the formulation, actually you're gonna see that the solution for this is actually very simple, just like adding one line of the code in the denoising the process. You're gonna see how it basically works. So let's first basically think about some easy case first. So think about whether the A function is basically linear function. So linear function basically means that it's just like a matter of like multiplying some kind of the matrix to the x0 here. Basically some kind of the output that we want to see. So as you can see, like we want to generate the x0 as the output of the denoising the process, while basically the measurement y is kind of given as the condition, as the input, right? And the relationship between the x0 and the y is basically represented with the matrix A here, when the A function is basically linear function. And as you can, actually, the thing is that most of the applications that we discussed in the previous slides are basically the cases that A is actually a linear function. Like all the convolution or the interpolation or the masking projection like these are all the cases that we can represent the relationship from the X to the Y as kind of the matrix. So you can think about these are basically while we are basically seeing some kind of the specialty case, actually this can cover most of the applications that we discussed before. Clear? So based on that, what we are going to say is that as we have seen in the previous quiz, when we basically have these two conditional distribution, like y from the given the x0 and from the x0 to the xt, now we can basically see that the conditional distribution from of the y given the xt can be modeled in this way. Does it make sense? So here, basically, one thing is that at the end, basically, what we want to see is basically the conditional distribution of the y given the xt. And from the relationship from the x to the y here, the only information that we can basically get is basically the conditional distribution of the y from the not the given the xt, but x0, right? You can see here. So from the property of the Gaussian distribution, since the z is basically the sample from the unique Gaussian, from the properties of the Gaussian distribution, what we can easily see is that the conditional distribution of the y given the x0 is basically can be seen as kind of the simple Gaussian distribution like this. But here the thing is that what we need is basically not exactly y conditioned by the x0, but actually we need the information about the y conditioned by the xt in a way that we can add some kind of the guidance at the every denoising step. So what we do is that we are modeling this another conditional distribution of the x0 conditioned by xt using the Tweedie's formula by taking the mean from the Tweedie's formula and adding some kind of some arbitrary variance here. So let's assume that this another conditional distribution like x0 from the xt is another Gaussian distribution in a way that we can also derive some kind of the approximation of the y given the xt. This makes sense? If you are not clear with this, I recommend you go back to the quiz and the answer for that and see how we can derive those things. So those are basically some of the output that we could see from the quiz 4. So you can check that out. So the thing is that when the information about the probability of the y given the x0 is basically given into this Gaussian distribution, and when you also model the conditional distribution, the x0 given the xt using another Gaussian distribution, now we can approximate this specific conditional distribution y given the xt using another Gaussian distribution, which is basically having this mean and the variance here. So you can see that the mean becomes some kind of the scaled Tweedie's output, scaled by the matrix A here, right? It's some kind of complicated variance here. Then as we have seen in the previous slide, what we basically need is basically about the score function of the y given the xt. So since we can now model the distribution of the y of the given the xt, it's just like a matter of like computing the gradient of the log of like this probability. So it's like if we do some kind of a calculation, so let's like simplify the notation in terms of that we denote this entire variance as the big sigma here. And then we first take the log of the probability distribution here, and then taking the gradient of the log of that probability, then we can see that now the score function can be calculated in this way. From the chain rule, what you can see is that now we are calculating this factor. And if you also see this factor, this is basically nothing but taking the difference between the measurement and also the kind of the prediction of the x0 multiplied by the a here, right? So what you can say is that this x0 by t is the prediction of the x0 at every time step t, right? And from this, like now we can see how the output of the measurement should look like by multiplying the a here. And we basically see some kind of difference between the real measurement that we are and also getting the observation that we are getting from the prediction. And this difference is basically multiplied by some kind of scaling factor here. And also we are basically multiplying the gradient of the Tweedie's with respect to the xt here. So we have seen that like how we can get the kind of expectation of the x0 at the given the xt using the trees formula, right? So now you can see the idea in terms of how we can calculate the square function of the y given the xt. Make sense? So from all the kind of the calculation, now what we can see is that especially like if I go back to the previous slide. If we model this specific the conditional distribution, that's kind of the x0 condition by xt as like this Gaussian distribution, so we can calculate the mean here. The thing is that we are basically giving some kind of the arbitrary variance here as kind of some isotropic variance. So if we model this conditional distribution in this way, then from this specific assumption, now we can calculate the square of the y given the xt. And it's basically a matter of like basically modifying our basically the noise prediction with this kind of the extra the scope, the term, in terms that we are giving some kind of the guidance in the denoising the process. Does it make sense? And this technique is called the pseudo-inverse guided diffusion models because like if we think about the special case that there is no kind of the corruption in our the measurement, for example, like for many of the cases like the super resolution or some kind of the so image in painting case, we can assume that there is no kind of the noise in the measurement. In this specific case, that this scaling term for the difference between these two becomes some kind of like multiplying the pseudo-inverse of the A here. So you can say that like this is basically multiplying some kind of pseudo-inverse of the A here into the some kind of difference. So that's why this is called the pseudo-inverse guidance. Is clear? Any questions on this? And now we are also going to see even a simpler version of this. So previously, like we assumed that the variance of like this conditional distribution as kind of the R squared, right? So let's assume that now the variance is zero. Think about some kind of special case like when the variance is basically zero. Then this basically is the case that the conditional distribution becomes some kind of a Dirac delta function, like zero variance. We always get the mean as kind of the sampling in the outputs. So in this specific case, now what we can say is that now this like conditional distribution of the y given the xt is also simplified into this form. So we are basically dropping the like R squared times like A transpose term here in the variance here because like R is zero. So now we can see that the conditional distribution of like y given the xt even becomes simpler like in this way. And with this simpler the Gaussian distribution, let's also lift up basically the assumption of the linear function. So let's think about like any arbitrary A function. So now it doesn't need to be even like a linear function. Then we are also going to see this specific the conditional distribution, right? And from this, if we compute the square function, then this will basically have this form. The square of the y given the xt is basically also taking the L2 difference between these two and also taking the gradient of this basically the L2 the difference. So again, basically here, basically this term is taking the twist from the xt. We are getting the kind of expected value of the x0 and basically feeding this into the A operation. And this output should be close to y, right? So that's basically the output that we want to see. So we are measuring basically the L2 difference between the real the measurement y and basically the y which is obtained from the prediction of the x0, and then taking the gradient with respect to the xt with some kind of scaling term here. So this will be basically some kind of the offset of the square that we are going to basically add into our the noise prediction. Okay. And even what we can see is that how we can apply exactly this into our the denoising process. So let me also go back to the things in terms of the DDPM, the reverse process. So we are going to say the DDPM case here, but actually DDIM case is not different. So in the DDPM, the denoising the process, from given the xt, we first basically do some kind of the noise prediction here. Based on that, we get the basically expected value of the x0 from the xt. And then based on that, we compute the mean from this distribution and basically sample the xt minus 1, right? So if we see like all the steps in the one step of the denoising, that what actually we can see is that the xt minus 1, which is basically sampled from the xt, can be seen as kind of the like some affine function with respect to the some kind of the noise prediction here, right? So this is the predicted noise, and you can see that xt minus 1 becomes like multiplying some scaling factor into the predicted noise and adding some kind of the offset, right? So xt minus 1 is basically the affine function with respect to the noise here. In terms of that, we are just simply having some scaling factor here and adding some kind of offsets here. Right. Actually, while the formulation looks complicated, it's basically nothing but like multiplying some scaling to the noise and adding some offset, right? And here, basically, what we want to do is that now we are going to modify this noise, right? So now we are basically not just taking the unconditional score, but basically adding some kind of the conditional score as well. So which means that we are not just directly taking this noise, but adding some kind of the conditional noise factor here. And this conditional noise basically can be calculated by this core function that we just calculated in the previous slide. So if we can calculate the score of the y given the xt, now we can calculate this unconditional noise with some kind of scaling factor. And you just need to basically add this to the some predicted noise, right? So if we do like all these kind of calculations, like just like adding this additional noise term into the DDPMD formulation, then what we can see is that we are also modifying the xt minus 1, right? So let's say like xt minus 1 prime is basically the sample that we sampled without the conditional part. So let's say xt minus 1 prime is the basically sample at the time step the t minus 1 with basically the noise, unconditional noise here. So you basically first sample the xt minus 1 prime using the unconditional noise. And if we also get some kind of the xt minus 1 with the conditional, basically the score, the terms there, then what just need to do is that we just need to add this extra term, right? So you can see that this is basically nothing but in this formulation, we are replacing this unconditional noise into the summation of the unconditional noise and the conditional noise. Makes sense. Just replacing this score term, the noise term here, include the summation of the unconditional noise plus the conditional noise. And let's say that the xt minus 1 prime is basically the xt minus 1 the sample without the conditional noise, only using this part. Then we just need to basically calculate the offset, which is coming from this additional part, right? And what we can see is that it becomes basically adding this term, which is basically some kind of some scaled the gradient of the alto loss. So if we basically denote this scale term as some kind of the sign here, then what you can see is that it's basically nothing but taking the back propagation through the alto loss between the real measurement and also the observation coming from the prediction of the x0 here. And then basically, adding this kind of gradient term with some kind of scaling factor into the xt minus 1 sample, which is sampled without the conditional the part. Does it make sense? So you can check out those formulation. So interestingly, like what we can see is that adding some kind of the guidance through the y here is basically nothing, but we are just like running the denoising process as we have done in the some typical the DDPM or DDIM, the reverse process, and adding just like one line of the code, which is basically like adding some kind of the gradient for the alto loss between the real measurement and the observation coming from the prediction of the x0 here. So basically, by just like adding one line of the code in the denoising the process, we can basically expect to see some of the outputs, which is basically satisfy some kind of the condition given with some kind of the measurement y in the inverse programs. It is clear. So while we have seen kind of the lots of the formulations, you can see that at the end of all the things, the result is that we are just like adding one line of the code to do some kind of the guided degeneration. But obviously, kind of the limitation is that now we are basically using this approximation. Now we are basically modeling the conditional distributed x0 from the given the xt as kind of the Gaussian distribution. So now we can calculate the mean correctly using the Twist formulation, but the variance can be something else, right? And even actually, this distribution may not be a normal distribution. It can be another the types of distribution. We are basically approximating this conditional term as the another the Gaussian distribution in a way that we can basically easily calculate all the things. But basically, we are basically using some very strong the assumption in terms of like modeling this as the Gaussian distribution. And especially for this algorithm, like just like adding one line of the code here, even we are assuming that this like the variance is also zero. So now we are also assuming that this distribution is kind of the Dirac delta function, which can be too strong assumption. It may not be true for most of the cases. So because of the effect of that, actually the output may not basically satisfy the given the condition, given as the y there. And then also basically lots of the work in terms of basically how we are going to solve the inverse problems better using the pre-trained the diffusion models. So if you are interested more about those things, you can check out some literature like this paper. And there is also even some kind of survey papers, which is also summarizing all the recent work. So this is really based on the very recent research, basically solving the inverse problems using the diffusion models. I recommend you to check this out for some more information. And I have some few more slides about like how we can basically apply this idea for the many other applications and how we can also choose like which method for which type of some conditional degeneration. So I'm going to wrap up the rest of the slides on Wednesday, and also I'm going to do some kind of we're gonna have some kind of some orientations for the course project next Wednesday. Any questions on this? So if you had any kind of the difficulties, like following some kind of some equations and some formulations in the slides, I strongly recommend you to basically go back to quiz that we had today and see some details there. I think it'd be really important to understand some more details rather than just like adding some kind of the line of the code in your implementation. Okay, so I will see you next Wednesday.